So we have our Coke can that has a height of 12.2 centimeters. So we'll go ahead and label a few things on here. And so this dimension here is going to be 12.2. And we are going to assume that everything is perfectly cylindrical and that the radius of this can, so from that point to any outer edge, is going to be the value of 3.25 centimeters. Okay, well, what we do know from geometry is that the volume of a cylinder has a formula, and the volume is equal to pi r squared times the height. So pi r squared is the area of a circle, so that can be thought of as the area of maybe the top surface, if you will, and then times the height, well, it's as if you had a bunch of those circles stacked together. So the volume is the pi r squared height. Okay, now it might be tempting. Well, let's first of all write this in function notation so we have something off of which to go, and again, we'll just write them in the order that the variables appear to keep things simple. And what might be tempting right now is to, well, we could verify that the volume is 355 centimeters, so I'm going to assume that we're fairly close. These are dimensions that I grabbed off the web, so if you take 3.25 and 12.2 as the height, then you should get approximately 355. Okay, so centimeters, you have r, which is measured in centimeters, so centimeters squared is centimeters, and centimeters squared times centimeters gives us centimeters cubed, and cubic centimeters are the same thing as the unit of milliliters. So now we have this function here, and again, we can now proceed to think about its partial derivative. So does it make sense to increase radius by 1 or height by 1 centimeter? Well, an apparent way to answer this question would be to, okay, well, let's just plug in 4.25 and let's plug in 13.2 into two separate equations and see what the volumes come out to. But we're going to do this the partial derivative way. So the partial derivative of volume, if we were to change the radius, would be the derivative of this function here. Okay, so again, what I'm going to do before I take this derivative is rearrange it in such a way that I bundle my constants, or I shove my constants to the front, push them to the front. So because r, I'm looking at the change in volume with respect to the change in radius. So what we want to do is graphically look at, well, how does the volume change as you increase the radius? And we're going to treat height as a constant. So height is a constant. Push those to the front. So it's really constant times r squared. Well, this is the same thing as taking the derivative of, let's say, 6r squared. What would that be? Well, that would be power by the power rule, 6 times 2r to the first power, or 12r to the first power. Well, in this case, we're leaving h untouched, and so pi times h is a constant. So instead of 6, we would have pi times h times 2r to the first power. That's the derivative of r squared. And so the change in volume with respect to the change in radius function will be pi times h times 2r, or 2 pi hr. Okay, now we'll do the same thing. Before we actually assess which ones, before we plug in any numbers, we're going to take our partial derivatives. And the partial derivative of volume with respect to treating h as a variable. So now it's as if we wanted to take a look at a graph of what happens to volume if I leave the radius fixed, but I change the height. Okay, well, same idea, except now my constant is r. I'm leaving the r untouched, and I'm seeing what happens if I change the height. Okay, well, now I have a constant times a variable to the first power. That's the same thing as asking what's the derivative of, let's say, I don't know, 12r to the first power. Well, that's a linear function right there. So if you want to use the power rule, I suppose you can. 12 times 1 to the r to the 1 minus 1. And that's going to give us just 12r to the 0, or 12. So we don't really need to take the derivative if it's to the first power, because that's a linear term. Okay, so that means that if, in this case, my coefficient of the variable to the first power is this quantity here, then the rate of change of that is just the constant quantity there, pi r squared. So now I can think about what's going to happen if I increase my radius by 1. Okay, well, first of all, we want to be taking a look at the instantaneous rate of change at these two figures here. So another way I could write this to make it a little more sensible is to write the derivative partial of v with respect to r as v sub r of rh, and that is equal to what we just calculated, 2 pi hr. Okay, so now if I wanted to look at, well, what will the volume change by if I treat h as a constant, and right now the height is constant at 12.2 centimeters, and my current radius is 3.25, so this function will tell me what the volume should change by if I increase the radius by 1. Okay, well now I'll plug in my numbers, 2 times pi times the height, which is 12.2, times the current radius, which is 3.25, and I'll do the math on this. I'm just going to use GeoGebra's CAS view, and in here I could type in the function that I have, which is 2 times pi times 12.2 times 3.25. Okay, well, it's going to give it to me in exact form, so I need to switch to numeric approximation, and that means that I get an output of 249.13. 249.13. Well, what does that mean to us? Oh, 249.13. Well, this is a rate of change. This is the change in volume with respect to a 1-unit change in radius. So let me write it over here because I'm running out of space. 249.13 is the same thing as 249.13 over 1. Okay, well that's what we just calculated, which is the change in volume per change in radius. Well, if I increase the radius by 1 centimeter, then I'm going to increase the volume by 249.13 milliliters, or cubic centimeters, same thing. Okay, so now I know. At that instant, at the current dimensions, I anticipate that a 1 centimeter increase in the radius will lead me to a 249.13 milliliter increase in the volume. I'm going to do the same thing now. So this doesn't answer the question yet. We want to know, does it make more sense to change the radius by 1 or change the height by 1? Well, here's the function that's going to tell me what my volume should change by. And again, I'm going to convert this to the function notation form. Well, this is the partial of v with respect to h as the variable, and the function that we just calculated is pi r squared. Great. Okay, so if I plug in my current dimensions to see what would happen if I increase the height by 1 unit, I'll plug in 3.25 and 12.2. Well, first off, note that the derivative of, or the partial derivative of volume with respect to height does not include h in it anymore. So the rate of change of volume as you increase the height does not depend on the current dimension of the height, which is interesting. So that's just a mathematical relationship to us for now. And so because there's no h in this formula, it really doesn't matter what this number here is, but it does matter what r is. R is 3.25. If I square that and multiply it by pi, I will get, let's see, plug that in here, pi times 3.25 squared gives me 33.18. 33.18. Okay, so we get approximately 33.18. Well, what does that mean? Well, again, this is just the same notation as this notation here. So this means that 33.18 is the same thing as 33.18 over 1. And since this is treating height as the variable, this means a 1 centimeter height increase will only lead to a 33.18 unit or milliliter change in the volume. So even though I'm looking at increasing the radius by 1 or the height by 1, the radius leads to a huge change, whereas the height only amounts to a tiny change. How can this be? Well, if you increase the height by 1, then really all you're doing is you're creating an extra sort of small little cylinder here that looks, I don't know, like about this. So all you're doing is you're changing that, and you're adding just this little bit of Coca-Cola here. But if you increase the radius by 1, then you are actually changing the entire dimension of the original can, and the entire dimension here. So you're actually getting a lot more volume by and this is all the way around, by the way. So all the way around, you get this little extra pocket of Coca-Cola, and if you surround that, it's like kind of like a Brita filter. If you've ever seen a Brita filter, the Brita filter is in the middle, and you can put water around it. This is as if you kind of have, like, put the Coke can within a Coke can. Then you get this extra bit of volume all the way around that can, and that amounts to a whole lot more than just giving 1 more centimeter of height. Is this always true? Certainly not. Depending on how big our radius already is or how small it is, if the radius is really small, then increasing it by 1 centimeter may not lead to a big volume increase. So that's something to keep in mind. We can answer additional questions with this. Okay, so again, an exploration of partial derivatives. Let's look at some other rules. So product and quotient rules. Product and quotient rules apply to when we are trying to take the derivative of a product of functions. Now, it's instantly tempting for us to just say, oh, well, I just take the derivative of the first function, take the derivative of a second function, and mash them together. Not true. Actually, if you have the product of f and g, both of which have x in it, then the derivative is the derivative of the first times the second plus the first function untouched times the derivative of the second. So f prime g plus fg prime. It kind of flows if you say it enough times. Okay, so let's look at a couple of examples. Oh, and quotient rule is very, very similar, except it's f prime g minus fg prime times g squared. In this case, it doesn't really matter which one you call f and g because there's a plus sign between them, and you're taking the derivative of one in the first term and the derivative of the other in the second term. But here it does matter which one you call f and g, because the way we've written it is f is in the numerator, g is in the denominator, and if you mix them up, then you put the wrong function in the denominator, or you flip these two terms around, you're going to create a little bit of a headache there. So find the partial, before we do that, let's just take a look at a simple example with a single variable case. So let's say we're trying to take the derivative of, let's say, x squared times 2 to the x. Okay, well, this is a function of x, and this is another function of x, and they're being multiplied together. So we'll call this one f, and we'll call this one g. And so what I like to do is I like to write off to the side what is f and what is g. And then right below that, I like to say, well, f prime, the derivative of a power function, is 2x, and the derivative of an exponential function, again, constant is in the base, natural log of 2 times 2 to the x. And now I can put it all together. So the derivative of this is going to be f prime g. Well, f prime is this. And if you look at the kind of the structure, it's a diagonal structure if you've written it this way. It's the sum of these two circled products. So f prime g is 2x times 2 to the x. And now fg prime plus fg prime, which is x squared times the natural log of 2 times 2 to the x. And if you've written it in a different order, like you put the natural log of 2 out front, that's fine. It's the exact same thing. Well, what's the difference if it were x squared over 2 to the x? The only difference is that now my formula calls for f prime g in the numerator, which would still be 2x times 2 to the x. But now it's minus fg prime, which is x squared times the natural log of 2 times 2 to the x. Now, all of that is divided by the square of the denominator, which is 2 to the x squared. And we're done. That's it. Partial derivatives apply in much the same way. They just look messier. Now we're taking the derivative of this, treating y as the variable, x as a constant. It's just a number. Okay, well, there are a lot of ways you could treat that x in there, but we'll just go ahead and use the product rule in the simplest form we can, which is, okay, well, y squared is a function of y. That contains a variable. And then x times the natural log of y contains a variable. And so we'll go ahead and say that f is equal to y squared, and we'll say g is equal to x natural log of y. And this is just a constant right here, so I'll box that up so that f prime is equal to 2y, and g prime is, well, it's a constant times the derivative of the natural log of y is 1 over y, or you could just write that as x over y. And I put it all together, I get f prime 2y times g, which is y squared, g is x natural log of y, so I'll take that back, x natural log of y, plus fg prime, which is y squared times x over y squared times x over y. And that's it, we're done. If you wanted to do a little bit of reduction here, you could make this 2y natural log of y plus